Hi everyone, today we'll be going over exceptions to our typical Lewis structures. Following the original rules is a great thing to do when you're drawing Lewis structures, but these are just some exceptions that are kind of common that you should be aware of just so that you're not surprised later on. There are three main types. We have first electron deficient molecules. And I'll abbreviate molecules as MC. We also have expanded octets. And free radicals. And we'll go through an example of each one. So electron deficient molecules, some that you might see often are hydrogen, beryllium, and boron. I'll underline these so that we can keep it separate. And one example using boron is boron trifluoride. So let's just try drawing this out and see what happens. So boron has 3 valence electrons that we know of from the periodic table. And fluorine has 7, and there are 3 of them. So when we add this up, we get 3 plus 21, 24 electrons that we need to use up in our structure. We'll put boron in the middle since it's the least electronegative, and those tend to go in the middle. And just attach all of our fluorines to it. And let's go ahead and give everything a completed octet as well, and then see where we are at the end of that. So notice that each fluorine is surrounded by 2, 4, 6, 8 electrons, and we have 3 groups of those, so we've used up 24 electrons in this structure. But this looks strange because boron only has 3 bonds on it, and you would expect it to also want a full octet, right? However, if we solve for the formal charge of each of our atoms, we'll start with fluorine. Our formal charge is 7 valence electrons minus 6 bonding minus 1/2 times 6 non-bonding minus 1/2 times 2 bonding. We get 0, so all of our fluorines are happy. Then when we solve for the formal charge of boron, boron has 3 valence electrons based on the periodic table. It has no non-bonding electrons here, and 6 bonding electrons. So this also comes out to 0. So since all of our atoms actually came out to have a formal charge of 0, they're all satisfied. And boron doesn't necessarily have a full octet, which is why we call it an electron deficient molecule, because the boron in the middle doesn't quite have as many electrons as we'd expect, but it is still happy and satisfied, and this is a plausible and the most optimal Lewis structure for this molecule. Moving on to our expanded octets, and let me just scoot this over a little bit so we have space. Some common molecules or atoms that you might see having expanded octets are sulfur and phosphorus. And we'll do an example using sulfur. We have sulfur hexafluoride. And let's try drawing this out. So sulfur has 6 valence electrons. Fluorine has 7 each, times 6 of them. We have 6 plus 42 gives us 48 electrons that we need to use up. We'll put sulfur in the middle since it's the least electronegative, and just put our 7 fluorines around it. Excuse my drawing skills here. We'll give all of our atoms a full octet. And then we notice that each fluorine uses up 2, 4, 6, 8 electrons, and we have 6 groups of those, so that gives us 48 electrons as well. But now this one looks a little bit weird because sulfur has 6 bonds on it, which is a lot, and it has more than the normal octet. But again, if we solve for the formal charge of each of these atoms, fluorine comes out to 0, and sulfur, which has 6 valence electrons minus 0 non-bonding electrons here, and then 1/2 times 12 bonding electrons also comes out to 0. So we can see that sulfur is satisfied with its expanded octet. So that's an example of an atom that you might see having an expanded octet in its Lewis structure. Lastly, we have free radicals. One common atom that you might see having a free radical is nitrogen, and we'll be using that in our example of nitrogen dioxide. Now this one is a little bit trickier, but we'll go ahead and start it the same way. Nitrogen has 5 valence electrons. Oxygen has 6, and we have 2 of them. Now this one is a little bit tricky here because this is actually an odd number, and usually we're working with electrons in bonding pairs or lone pairs, so it's usually an even number, right? So when we have odd numbers like this, we often see our free radicals coming into play, because a free radical is when an atom has just one singular added electron on it. But let's try drawing our Lewis structure the way we normally might, with nitrogen in the middle attached to our 2 oxygens, and we'll see kind of what the problem is. We give them all a full octet, and we find that we have a formal charge of -1, -1, and -1. Now, nitrogen is not really happy having a minus or a negative formal charge. If anything, it would rather have a positive formal charge. Oxygen is happy that way, but since we have a formal charge on every atom, this is not our most optimal Lewis structure. So we want to kind of move it around to see what else we can do. Additionally, notice that we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons being used up in this structure. So obviously this can't be our correct Lewis structure because 17 is a lot less than 20. So let's try something else. Let's go ahead and add in a double bond since we already know we have to reduce the number of electrons that we're using in our structure here. So I'll go ahead and just put it right here to try. Give everything our full octet. And now we have a formal charge of 0, -1 on this oxygen, and 0 here, which looks good, except we cannot have this many electrons. We still have too many. We have 18 electrons in this structure, so we need 1 less. So we're going to go ahead and take it off of this molecule here, or sorry, this atom here, nitrogen. And you see that this actually makes our Lewis structure look a whole lot better because now we have the correct number of electrons, which is the most important thing, right? So that's why this one could not be right and this one could not be right. So we have the right number of electrons now. And we've been able to get our formal charge of one of our atoms here, this oxygen here, to 0, which is great. And while it's not entirely optimal that we have a formal charge on these 2 atoms, since it's kind of impossible to get the formal charge of all of them down to 0, this is the best possible arrangement that we can have, because nitrogen does accept having a positive formal charge in some cases, and since oxygen is pretty electronegative, it's pretty happy with that -1, -1 formal charge. And so this is actually our best Lewis structure for this molecule, and it's an example of when a free radical might come into play. So again, our Lewis structure exceptions, we have our electron deficient molecules, our expanded octets, and our free radicals. So just be aware of those as you're going on and drawing your Lewis structures.